So again, here's our situation. We have an object traveling through space. It has clearly a momentum, and it is in space so that there's no external force acting on the system. Under those conditions, this object's momentum would remain constant for all time, for all points in the future. Even if I extend it to a larger system, I could have a system right now with another object of similar mass, but with a velocity straight up, even if it's the same velocity, straight upwards. These two objects together form a system. And in this system, there is a net momentum. Now, it's important for you to understand that that net momentum is likely in this direction, that this must be the momentum of the system. Because one object has momentum to the right, the other object has momentum to straight up. So there's a net momentum in that direction. Now, it is quite possible at some moment in the future, these two objects may come into contact. The way it's drawn, maybe not, but if this box had started a little bit sooner, they would come into contact. And it doesn't matter what the result of that collision is. If there's no external force, the direction of the momentum will stay in this direction, no matter what happens in this collision. The first box could rebound off of the second box, and we would still have a net momentum in this direction. Momentum is a conserved quantity, which means that if there is no external force acting in the system, the momentum of the system will stay the same. Now, I'm trying to emphasize external. Let's assume for a moment they don't interact, that there is never any contact between the two. But instead of it being in space, we change it and we place it on the Earth. So that one object has been fired horizontally and one object has been fired upwards. Under this condition, will the momentum of the system stay the same? Does this system conserve momentum? We have an external force now. Now, what makes something external to the system? That's been something I've been trying to impress upon you, and I think I've just created confusion. For a force to be external, it has to have certain qualities. For one, it has to act on both objects in the same way. And that seems easy, but it has to act on both objects in the same way. It doesn't have to be the same force or the same size, but it has to act on them in the same manner. That's an ambiguous term because I want to make sure it fits every situation. But the second thing, and this one is the most important, is that it has to act on both objects in the same direction. Now, I want to be very clear, very clear. I made that second condition up. But I made it up because it's an easy thing to see. And it's more likely to be the kinds of problems we will face. Both of these objects are going to experience a downwards force. One of them is clearly going to increase the velocity of the object, this one. Because its horizontal velocity will be unaffected. It's going to acquire vertical velocity. It's clearly going to increase the velocity of that object. Thus, its momentum will not stay the same. The other object, it's probably going to decrease the velocity for a while and then increase the velocity. This one clearly is not going to have the same momentum all the time. Thus, the gravitational force is going to change the momentum of the system. The system is not going to continue to have momentum in this direction. We can probably all imagine that that momentum is going to change direction after a while. Now, gravity's an easy one to see because it affects all the objects the same, but we could have wind blowing on both of these objects. It might affect the objects differently because we know that wind is air resistance and the wind currents don't have to be uniform. But clearly, if it's a windy day and the wind is kind of blowing through here in some kind of random, non-uniform way, that would be an external force on the system. Even though it might not be the exact same direction on everything, it has a general tendency to change the momentum due to something external to the system. So I would not expect it. I do want to be very clear, though, that an external force does change the kinetic energy of the system. It might not change the energy of the system, but it would change the kinetic energy of the system. Let's be careful. If it's a conservative force, it doesn't change the energy of the system. It converts the energy from one form to another. But every external force changes the kinetic energy of the system. Period. It must. It causes an acceleration, and acceleration is going to change the velocity, therefore the kinetic energy changes. We can only say that energy is conserved under those circumstances if it's a conservative force that acts in the system. Only then is our external force conservative and will conserve energy. All right, so let's get rid of gravity for a minute. Go back to having this be in space. And I want to talk about collisions. So that's really what today is supposed to be about, is dealing with collisions and angular momentum. There's clearly going to be a before and an after case here. There's going to be something that happens before. And if you want, we can have a during and then an after. Now, truthfully, I don't really know what's going to happen in the long run. I don't really know what the outcome is going to be. I know that likely after the collision, there will still be two boxes. That's likely. I don't think there's a chance that the box that's not moving is going to be going to the left after this collision. You guys pretty good with that? Is it probably terribly likely that the box will have some kind of velocity to the right? I'm not trying to trick you. It'd be hard after this collision for the box on the right to suddenly pass through the box on the left and be moving to the left, right? That seems unlikely. We kind of know how physics works a little bit. But the first box, I don't really know what it's going to do. I know it's going to probably have less velocity to the right. And the reason I know that those things have to be true is merely because the physicalness of this situation. If we consider the boxes again during, and this is where I would really pay attention. Well, you should always be paying attention, but let's consider during for just a minute. There's the point of contact. This is when there's an interaction. This is where an impulse is exerted. All the vocabulary words we've tried to work into our program here. Interaction occurs only through force. And we have a variety of forces that can be involved in an interaction. But during an interaction, the forces involved must be a Newton's third law pair. That's what makes it an interaction. In this case, it's very likely the force involved is a normal force. And the first box is going to experience a normal force to the left. This is due to the contact. That's going to reduce the velocity of the first box. That's why I know the first box is going to be either going slower, it's going to stop, or it's going to be going backwards afterwards. Those are the only possible outcomes. It's not going to be moving faster to the right. It can't. The direction of the force dictates what happens to its velocity. In the same way that the box on the right is going to experience an equal and opposite force to the right. The only options for its motion after the collision is for it to have some velocity to the right. Now, how much of each of those things happens depends on the interaction, on things that I can't easily decipher. There's just too many variables. I don't know how soft the surfaces are, which will determine how long the two objects are in contact. I don't know how much the surfaces influence each other during this normal force. I just don't have enough information. I can tell you, though, after the collision, the momentum is going to be mv. It has to be. No matter what, mv was the momentum before the collision. So mv has to be the momentum after the collision. You tend to forget that. You tend to think that I have to shape my momentum in terms of what is happening now. And that's not true. In this case, the forces that acted were internal to the system. They formed a Newton's third law pair. The only forces that occurred were an interactive force between two objects. Because of that, I know the momentum had to stay the same for the system. But I also know that each of the two objects changed their momentum. I could write that the momentum after the collision is actually mv1 plus mv2. That's fine. But I don't have to know what v1 and v2 are. And there's no reason to believe I do know what they are. Which is why knowing that momentum is conserved doesn't necessarily tell you that you know what happens during a collision. All the things we just talked about, all the forces that are acting, all the changes that occur, still don't tell us what v1 and v2 are after the collision. For that, we would need more information. We would need to know more about the collision or more about the results of the collision. Like them sticking together. That's a significant issue. They stick together, they have to have the same velocity. So v1 would have to equal v2. So they add things to the problem to make the problem something we can solve. But to the physics, the momentum after the collision had to be the momentum of just the first box. And be aware, this problem is very, very straightforward. The truth is, any interaction that involves a Newton's third law force still conserves momentum. The Earth and the Moon have a complicated dance, but the system conserves momentum because the force between them is a Newton's third law force. It's due to gravity. In that case, the force of gravity on the Earth is equal and opposite to the force of gravity on the Moon. That forms an interaction, and because it's an interaction, it conserves momentum. It could be said that these two boxes probably experience gravity. And if they experience gravity, that would be an internal force. But it still wouldn't change the momentum of the system. It might change individual momentums of objects, but not the system. Now, so we're going to start with far fewer things. But instead of our second object being small enough where its shape didn't influence the problem, we're now going to look at having our second object have enough extension, enough size, where the interaction is going to be influenced by the size of the object. And I think this is a good example of that. I think you guys can probably think, critically about what would be the result of this interaction. Let's assume that we are looking top down on this, that this is two objects that are on a frictionless surface like ice. What do you think the result of this collision is likely to produce in the two objects? So let's talk about the box for a minute first. What do you think the result of the box striking this rod will be? All right, so I think we can say that. We can probably say it slows down. I think that's all right. That's probably the easiest to suggest, that it will have a new velocity that is slower than before. All right, the rod. What's likely to happen to the rod? So, the rod will gain velocity, but let's be clear about it. Is the rod going to move in a strictly linear way after this collision? No, it is likely that after the collision, the rod will now have some kind of rotational speed. But it's also likely to have some linear speed as well. Now, before we go into this too much, there's probably something that you guys don't know that I've talked about it, but I've only talked about it in a relatively passing way. And I really need to make sure that we kind of nail it today. That if you throw something, just throw it and give it a spin, it doesn't just spin about some random point. Unless an object is given a fixed axis of rotation, objects will spin about their center of mass, period. I want you to try this weekend. Try and throw a Frisbee, but instead of throwing it the way you would normally do it, do the little flick with your thumb. You guys know what I'm talking about? A lot of people try and throw it with their thumb, like flicking it backwards. I'm saying that because if you're holding it by the edge, then you are creating an axis of rotation about the edge of the disc. If you let it go, it doesn't stay rotating about the edge of the disc any longer. The moment you let it go, it immediately begins rotating about its center. It won't stay rotating about its edge. This is true for anything. I would not recommend doing this unless you have a big enough place to do so, but grab a bat and just throw it. That's why I said I don't recommend doing this. But if you do so, the moment you let it go, like the instant while it's still in your hand and you're just about to open your hand, the axis of rotation is either about the handle or your shoulder. Like if you just have it in your hand, just kind of flick it like that, the axis of rotation will be right there at the end of the bat where your hand is. And if you do it from your shoulder and throw it, then the axis of rotation will be where your shoulder is. But when you let it go, it will spin about its center of mass only. It won't stay spinning about your shoulder. You understand why, right? That it's going to spin in such a way that there's equal mass on both sides. Because if there isn't, it would wobble and torque until it did. So all objects naturally spin about their center of mass. If you fix an object in place, it can have a different axis. So if this object is resting on the ice and there's a collision, then there must be a rotation about the center of the object. Now, here's the hard part of this discussion, the part that students have difficulty identifying. The rod now has angular momentum and linear momentum. And we know the linear momentum of the system because the linear momentum of the system is mv. Has to be the linear momentum of the system. There's no way it can't be because that was the momentum of the system before the collision. If you want to take this problem and look at that instant of the collision like we did before, take a look at the during part of this collision. There's the during part. And during the collision, the box experiences a force here. While during that same moment, the rod is experiencing a force and a torque. Now, the problem is in saying that the rod experiences a torque and the box doesn't. The box must also be experiencing a torque. because that is occurring due to the exact same force. The problem is that, how do we measure this torque on the box? The box doesn't rotate after this. The rod does. I mean, it's clear, it's easy to see that if the center of mass is here, there's going to be a torque arm length there. How do we quantify this idea that the rod now suddenly has angular momentum? And there was or appeared to be no angular momentum in the system beforehand. And we don't rectify this, not the way that you think we're going to. Instead of rectifying it by saying that the box somehow created angular momentum that wasn't there, we say that the box had angular momentum before the collision. Now, this doesn't make a lot of sense to students the first time they see it or the first time they understand it. Well, I'm sorry, if you understand it, then it does make sense. Students tend to have difficulty the first time this is presented to them. That somehow, how does the box have angular momentum before this collision? It wasn't rotating. And the answer is less interesting than it sounds. Look, if it was just the box by itself, and the rod never existed there, then we would never say that the box had angular momentum. We wouldn't. It doesn't make sense. It's not rotating about anything. However, in a bigger view of what's happening here, we can say that the result of this collision is to create angular momentum in the rod. So in a bigger view of this problem, we recognize that the box must have some angular momentum as compared to the box rod system. Meaning, we don't talk about the box having angular momentum on its own. We talk about the box interacting with the rod in such a way as to impart momentum and angular momentum during the conditions where there will be angular momentum after the collision. That's how this is discussed. So when we talk about the angular momentum of the box, we try to be very clear that the box only has angular momentum with respect to what's going to happen between the box and the rod. Remember, we're trying to find a way to make predictions about what happens in our environment. So the rules that we're using here are designed by humans to suggest how we can observe the universe and make sense of what's going to happen. So I want to use a specific example now. I want to get down to more of the nuts and bolts of this. I'm not going to change this very much. I'm going to continue to deal with a box of mass m and velocity v. But to make this a little more rooted in things we know about, I'm going to table this discussion till another time when we can actually get through all of this and feel like we know some things. All right. We were just getting started with this example here, and this is mimicking what you guys have for your problem. So if those of you who have a copy of the question or saw it on ESB, this is what it looks like, right? You don't have this picture exactly. First it's, I think it's a smaller ball or something like that there. Not a big difference, but still slightly different. And after the collision, they show that the ball leaves at some angle, but that the rod continues with some velocity and swings until it reaches kind of an upward position like that, where it comes to rest. Something like that, right? Here, let me at least make it the same height. There. So it's going to kind of swing upwards, coming to rest just like that. In the problem, they don't tell you much about the collision. They tell you a lot about what happens after the collision. And you're asked to work backwards. I would encourage you to consider the parts of the problem that aren't shown. To take your problem and break it up into, I would say, important steps. For example, there's clearly a part of this problem that wasn't shown, and that was the initial part of the problem. They don't have this picture here, showing the object as it approaches the rod. They also don't have that instantaneous moment where the collision actually takes place. That instant where the one object is in contact with the other, but we're said to say, or said to believe, that the collision is imminent. So right here, the instantaneous moment before the collision. Because then there's the instantaneous moment after the collision. And that's a little different, and it's one I really want to be cautious about the way we discuss it. I'm going to turn it just a little bit so that we can consider that the object has instantaneously begun to move. And the box, depending on the problem, may or may not have the same velocity it had before. It's going to experience a force, so it's likely to change its velocity. And the problem that you were given, you have some condition like this. And they tend to not fill in the gaps. So this is way before. This is the instant before. This is the instant after. And this is a long time after. Momentum conservation, as a rule, requires that there is no net force acting on the system. But there's clearly a net force acting on the system. Gravity is acting on the system, which means there's an external force acting on all the objects in the same direction. So technically, we would have to state that momentum isn't conserved. And here's where you have to really understand the thrust of the rule. During the interaction, this part right here, momentum's conserved. Overall, momentum is not conserved. But that instantaneous moment before the collision and after the collision, the effect of the external force isn't strong enough to change what happens during the collision. So for the collision, momentum is conserved. Now that's not an easy idea, trying to figure out when can I state momentum is conserved. So if you see a collision, momentum's conserved in a collision, period. During that interaction, momentum's going to be conserved. Now, if you don't see a collision, then determining whether momentum is conserved or not is going to be harder. You really do need to then take more time to consider whether there is an external force that is affecting the momentum of the system. But if there's a clear collision, then you can say momentum is conserved during the instantaneous moment of the collision. Now, I've said that like 4 different ways just now. Do you have it someplace where you can study that idea? You're going to need to. I do want to emphasize something about this question, though, that I hope you guys see. Energy is conserved in this question because the external force is gravity. And because energy is conserved due to gravity, there is gravitational potential energy that's in the rod after it swings upwards. Its center of mass changed height. Remember, if you see an object whose center of mass changes height, you should always consider conservation of energy. That also suggests that the rod had rotational kinetic energy just after the collision. This is how you determine what the velocity was just after the collision for the rod. Now, be aware, the center of the mass is at the center of the rod. So the change in height is based on how much the center of mass changed. Now, I'm going to leave that now, let you guys work that problem out a little later. I want to focus on an example that we can kind of put together to see how this works during the collision part. I'm going to use the same things we saw. We're still going to have the rod hinged at the top. We're going to say the rod has length L, hinged at the very top. It is a uniform rod, so we're probably looking at a moment of inertia of 1/3 ml squared. I'm going to use capital M for the mass of the rod. And I'm going to have a small point mass, velocity V, mass lowercase m, that's going to strike the rod. So we're setting up our collision. Now, in this particular collision, as with all collisions, what happens after the collision is largely unknown. We don't really know in advance how these two objects are going to interact. It will depend on the hardness of the objects, the nature of the force of interaction between them. There's all sorts of things that are going to happen during this collision that we really can't anticipate. So generally, we have to have something to know after the collision in order to deal with a problem like this. In the prior one, they tell you how far the object went upwards so you can get the velocity of the rod. What I'm trying to impart to you is that in a collision, there's a lot of unknowns. And not knowing how they interact usually means you can't predict the outcome particularly well. So problem writers cheat. They give you a false piece of information that they know after the collision so that you have enough information to deal with the problem. Like they'll give you the velocity of the box after the collision, or they'll say the box will stick to the rod after the collision. These are things that they do so that you can solve a problem. But in nature, you may not be able to predict the outcome of an actual collision. There's just not enough information present for you to do so. But this is, a class with tests. So let's consider that in the example I would like you to do, the box sticks to the rod after the collision. And in so doing, there is kind of this box-rod system after the collision that is still rotating about this mutual point of rotation, and it's going to begin to swing upwards. And we're looking for the velocity of the system after the collision. This is a very traditional, straightforward, angular momentum collision question. So, to get this problem started, I want to remind you that we are interested in the momentum of the system and the angular momentum. We're going to try and figure out which one of these is conserved. I want to be careful here. On Friday, we started talking about angular momentum. As a definition, angular momentum is R cross P. R is measured from the axis of rotation to the object. I also want to remind you that if all we had was the object by itself, there really isn't an angular momentum to speak of. That if there's one, this object's going to hit the rod. So I'm going to use this point in space as the appropriate point of reference. It's the only reason to measure this object's angular momentum. It's as it pertains to the way it's going to interact with the rod. Otherwise, no, it doesn't really have angular momentum. It doesn't make a lot of sense. It has to have a useful purpose. Now, I do want to point out that we did go over what this means. The angular momentum is R times P times the sine of the angle between them. And we went one step further than that and recognized that R and phi are always changing, but they're changing in the same proportion all the time, which means this can also be written as r perpendicular times p, which I called in class the closest approach. It's a point of closest approach. In this problem, that shouldn't be a huge surprise that the object is going to hit the rod. And because it's going to hit the rod, my point of closest approach is the rod. Right there. It's going to strike right at the bottom of the rod. So because it's going to strike right at the bottom of the rod, I can use the length of the rod as r perpendicular. That is going to happen almost all the time. That the size of the object involved in the collision is going to show up in your problem. So we're almost always going to use the r perpendicular distance in calculating angular momentum. Look for it. We're almost always going to use the r perpendicular. Try and look for it. So that's what we're going to use here, the angular momentum before the collision. This one's pretty straightforward. R perpendicular is going to be L and then MV, and you're done. Because the angle is 90 degrees in this collision. Now, during this collision, is there any net force that acts on the system? I answered this on Friday, but it was towards the end of class. So I'm not sure you got it in your notes. There is. And I'm not just talking about gravity. There is a net force, an external force that acts on the system. And again, I'm not just talking about gravity. When we fix the object in place, we do so by pinning it to a location. That's what we did here. This could be a meter stick where I've put it, through a nail into the wall. Or if we're looking top down, say on something that's on ice, which is the problem we were doing on Friday, same idea. If this is a frictionless surface and I pin the object to the ground, there's an external force there. When the mass strikes the rod, there's going to be a force in this direction on the pivot. This keeps the rod in place and doesn't let it drift across the ice. It allows it to spin about this point, but not leave this location and move across the ice. This external force acts on the rod. And if the box joins the rod, it acts on the box too. Which means momentum would not be conserved in this collision. Momentum would not. Meaning this system will not have a linear momentum after the collision. The system is not going to continue to drift with a momentum in this direction because the object is stuck to the ground there. There's a big nail holding it in place. On the other hand, this force acts at the pivot. Because it acts at the pivot, it cannot cause a torque. Because a torque requires that any force act at some distance away from the pivot. So although the net force on the system is not zero, the net torque on the system is. Because this force acts at the pivot point. You will be asked this question on the exam to explain why or if there's an external force acting on the system. The answer is yes. But that force doesn't cause a torque. Therefore, the angular momentum is conserved. That's the important takeaway. Linear momentum, not conserved. Angular momentum is conserved. So, your next job is to now figure out how to use the angular momentum of our system to figure out what the angular velocity is. So I'm going to wait a moment because I think that second part you guys know how to do because you've made it past this part of our class already. you should be able to give me an expression for the angular momentum after the collision. I'm going to give you about 40 to 60 seconds to do so. Let's see what we have to do here. So, Jake, how is this different?
You can't combine like the two moments of inertia like we did in the Boston where we did the 1/3 ml squared plus ml squared because the box is going to be going at a different speed than the rod.
That's right. So, well, pick one of them. How would I deal with one of these?
You could probably keep the rod the same with the 1/3 ml squared with omega.
Okay, so if I was to get my angular momentum of the system, I'm just going to write it over here because it's a little higher up and more people can see it. I'll have the rod first, 1/3 ml squared. So, times omega?
Yeah.
Great. So, let's see, who else? Jason, what do you think I would do next?
I would find the angular momentum of the box.
Excellent. How would I do that? Do you know?
And V final.
What'd you say? Maybe I missed part of what you said.
M.
That's going to be the linear momentum of the box. The angular momentum of the box, we still have to deal with the fact that it's an angular momentum, so we need the value for R still. So if it just recoils right off the bottom of the rod, it'll just be L. We don't know what its new velocity is, so we'll just say V after. So I'm going to say lowercase m V after, but I do have to take into account the angle now because the box recoils at some angle. Be careful here, though. The angle I gave isn't the angle that you need because it's got to be the angle between R and the velocity, and that has to be this entire angle here. So that would be sine 90 plus theta. Oops. So make sure you have the whole angle there. Look, now you have everything you need to do that problem that you have for homework. I need to see it tomorrow, please. What we have is just an object in space, chilling with some velocity, roaming through space. Would we say that this object has angular momentum? Unfortunately, the technical answer is yes. It does, technically. The problem is that if our angular momentum is r cross p, what's r? There needs to be a point of reference. Now, I can create a point of reference and state that this object has an angular momentum relative to point P that exists right there in space. And that the object's angular momentum is in this direction, because it's got to be a rotational direction. And we know is a constant as it moves because r is changing and the angle is changing all at the same time. But the truth is, it also has an angular momentum relative to point, I don't know, Q. But that's a different r and a different angle, and therefore a different angular momentum, suggesting that a single object roaming through space would have an infinite number of angular momentums. But as I've tried to say, and this will be like the 6th time I've said this, angular momentum for a point particle only makes sense in relation to what that particle might do in the future. It doesn't have an infinite number of angular momentums. It has an angular momentum about a single point in space, one that makes sense for what happens to the object. So there's not an infinite number.